All right, so let's get to number 21. And with number 21, we have some reaction conditions. If you look at the first step, we're going to use a rather strong base. And then the second step, we're going to use water, which usually acts as an acid. This is a classic Claisen condensation. It is even further emphasized because this is going to be an alkylation reaction of an ester. You can see the ester is right here. And of course, this proton is going to be the most acidic because it's sandwiched between two carbonyls and has extra resonance stabilization. So, kind of take you through the mechanism of this reaction. It's a good review for the final. And we're going to simply generate the carbanion. I'm not going to show the resonance structure. We've already discussed this at length in class, that the carbon-oxygen double bond is far too stable for the negative charge to be isolated on the oxygen. So rather, it is isolated on the carbon. Of course, here is our carbanion. Now, we have to ask ourselves, what is the most likely ring to be formed? So let's start counting some carbons. 1, 2, 3, 4, 5. If we do conjugate addition, if we do the Michael reaction, we'll make a 5-membered ring. 6, 7. If we do more of an intramolecular aldol, we'll make a 7-membered ring. The 5-membered ring is more stable, therefore we're going to do a Michael addition, and the relevant arrow pushing is going to be this one right here. And of course, this will simply pick up a loose proton that's in solution, which we provide in step 2 of the mechanism. And so I think numbering these carbons is important to do. And so we have our 6-membered ring will be in place. We will also have a 5-membered ring. So recall that this is carbon 4, this is carbon 5, this is carbon 3 and 2 and 1. And also bonded to carbon 1 is going to be the methyl ester. And of course, carbon 2 also has a carbonyl. So remember, one of the hallmarks of a Michael is that delta keto carbonyl. So we have an alpha, we have a beta, we have a gamma, we have a delta keto carbonyl. And it's delta keto relative to this carbonyl or relative to this carbonyl. So now let's start looking at our answer choices in number 21. And you should clearly see that the best answer choice is going to be C. What I want to do is just scroll this enough so we can look at both of these documents at the same time. And you clearly see that answer choice C should be the credited response. So for number 21, the credited response is answer choice C. Moving on to question number 22. We have a spectroscopic problem, and notice that we're given a little bit of chemical information. So we have an oxidation product that gives a positive silver mirror test. That means that that's a positive test for aldehydes, which means we must have a primary alcohol. and that eliminates choice D and C and B. The answer must be A. Here's your broad OH. There is no carbonyl. And of course, you see the chlorine with your 3:1 ratio. The answer for number 22 is A. Now we have an interesting reaction of an alpha-beta unsaturated carbonyl, so the product of an aldol condensation. The Gilman reagent undergoes conjugate addition, so it will attach to the beta carbon, and the propyl bromide will attach the propyl group to the alpha carbon. So you can eliminate A, B looks good, you can eliminate C because it's reversed, and you can eliminate D because no direct addition should occur. So the best answer for number 23 will be answer choice B. Again, that's a Gilman reaction followed by an alpha alkylation reaction. You're looking for a base peak at 170 mass per charge ratio. Let's take a look at this one in terms of some chemistry we've already seen. So for number 24, we already know that if we have a benzylic group, that we can create the benzyl cation, and this benzyl cation will rearrange to give us an aromatic intermediate called the tryptopylamine. The tryptopylamine is aromatic. This has a mass to charge ratio of 91. Our base peak is at 170. So 170 minus 91 is 79, which happens to be one of the isotopes of bromine. So we can imagine that at some point on this ring we have a bromine and we have a good leaving group for X. Now that we have an idea what we're looking for, looks like A is the perfect answer for us. The chloride leaves, leaving us with the tryptopylamine ion precursor, and the bromine's already attached. The best answer for 24 is going to be A. Moving on to number 25. Number 25 is a question that relies upon your knowledge of nucleophilic aromatic substitution. You must have a good leaving group that's either ortho or para to a strong electron withdrawer. So D should be eliminated because fluorine is not a good leaving group. A should be eliminated because the methyl group is not an electron withdrawer. And nitro is better than an acyl group. So C is the better answer for number 25. So number 25, the best answer choice is letter C. Now 26 is interesting. We have obviously para substituted aromatic rings from the multiplets, the doublet of what appears to be a doublet of doublets. And by the way, when you see this leaning, so you can draw a line that leans from the lower left to the upper right, and one that leans from the lower right to the upper left. So if you were to connect the dots, so to speak, you'd make a roof to a house. That's real typical behavior for a para-substituted aromatic ring. Also, we see a singlet, and we see a quartet, and we see a triplet. The triplet and quartet appear to have equal coupling constants, so we should expect an ethyl group. There does not appear to be a broad singlet for an OH. And so if we start looking at, of course we don't have any integrations now, so we would have a triplet, we would have a quartet, we would have a singlet, that works. But notice this integration is actually fairly large for number 2. So let's see what we can begin to eliminate. If we look at the methyl ether, this singlet, since it is alpha to an oxygen, these hydrogens are attached to a carbon that is alpha to an oxygen. This chemical shift should occur at about 3.7 to 4. The singlet is at 2, so we can effectively eliminate C. Also, if we look at this, of course, this singlet is okay. This singlet would also be expected to be at 3.7 to 4, and it's not. It's at 2, so we can effectively eliminate A. So now we're left with a choice between B and D. And this is going to come down to our integrations. And so you'll notice that the 2 certainly has as much of an area under the curve as the triplet that would be associated with a methyl group. Therefore, the singlet should correspond to 3 hydrogens, not 2. We eliminate D and we choose B. That's a pretty discriminating question when all you have is your proton NMR. So the best answer choice for 26 is choice B. Aromatic compounds, obviously the 1,3,4-oxidizole is one of the lone pairs of oxygen adds to the ring, so you have a 6-pi system. So 1 is part of the answer. Of course, we knew that already. 2 is non-aromatic. This carbon's sp3 hybridized. Once you know that 2 doesn't belong, you eliminate A and B and C. The best answer must be D. This is the amino acid histidine. Wittig reaction number 28. Simply replace the oxygen with the double bond that's attached to the phosphorus. The driving force for this reaction, remember, is the formation of a phosphorus-oxygen double bond, and the best answer is going to be choice A. So 28, the credited response is A. 29, the major resonance contributor is going to be C, because it goes to the position that is alpha to the sulfur. When it is not alpha to the sulfur, notice there's no place for a positive. The positive charge would be on a sulfur, and you really need to explore with how many of these resonance structures that one can draw. This sigma complex will yield another resonance structure where the double bond could be here, and this double bond becomes a lone pair. It is very difficult to draw another good resonance structure for B, so C would be the credited response. And it is a point of fact that the substitution pattern when you nitrate a thiophene ring occurs at carbon 2 and not at carbon 3. So 29, the credited response is C. This is an interesting spectroscopy question. There are only 2 environments, and they each integrate to 6 hydrogens. It must be A. These 2 are identical. These 2 are identical. These 2, of course, are closer to the oxygen. They're this environment at 3.2, while these 2 are upfield, and they will occur at about 1.3. All right, so I'm going to cut this one short now, and I'll pick up with the next one on question number 31.